Typically, density-dependent factors intensify as the population size increases. A very well-known example is salmon and the spawning of salmon. When salmon, like in this image, are moving upstream to spawn, they lay their eggs in the gravel and the sand. And when there are hundreds or thousands or hundreds of thousands of fish that are moving through there, there could be so many salmon that they actually wipe out the nest of other salmon as they come through there. So with a species like this, they actually will have a higher nest success rate, a higher probability of those eggs actually hatching when the population's low versus when it's high. So this is very well documented with salmon and with many other species. There's similar examples. There are several factors that can regulate population growth. Intrinsic factors would be those things that operate within an individual or within individuals of a species, such as age of first reproduction, average litter size, the limit on how old an animal can get. For example, an elephant. African elephants don't reproduce until they're between 9 and 12 years old. Because of that, that limits population growth. They have to survive at least 9 years before they even have the potential to reproduce. This would be an intrinsic factor that regulates population growth. Extrinsic factors might be things that are happening from outside of the population. Like in the case of elephants, people might shoot elephants when they're larger and when they're in their reproductive prime because the ivory is larger at that point. Biotic factors would be things that are caused by living organisms. These are very often density dependent. So things like the salmon that are wiping out the nest of other salmon, that would be a biotic factor. The food resources that are available for species. So for white-tailed deer, a biotic factor might be understory in a forest, and understory in a forest can become limiting as the population gets high. Abiotic factors would be things from the non-living environment. These would be like, it could be weather events, rainfall, storms, catastrophic events. It can be limited denning sites, or even just space for animals. I gave the example last time of a fishbowl, and that within a fishbowl you can only have so many goldfish because there's only so much space. That limiting space would be an abiotic factor that can regulate population growth. Density dependent factors, by and large, reduce a population size by decreasing natality, which is reproductive potential, or increasing mortality. Most of those density-dependent factors break down to those two elements. Intraspecific interactions would be things that happen between two different species. So predator-prey oscillations are a good example of that. Canada lynx and snowshoe hare are a classic example. As snowshoe hare populations increase, that provides resources for Canada lynx. Then the Canada lynx population will expand to take advantage of those resources of lots of rabbits. They eventually deplete that resource. There's less rabbits available. That supports less lynx, causes the population to die off. As the lynx population dies off, then rabbits are able to bounce back, and you end up with this oscillation. These are pretty classic oscillations, pretty well documented. I'm noticing in this image that's actually a bobcat, not a Canada lynx in your textbook. There are intraspecific interactions that are density dependent as well. These would be competition for resources between individuals within a population. So deer, for example, competing for the same browse, that would be an intraspecific interaction. As a population approaches carrying capacity, one or more of these resources become limited. And this slows down population growth and helps to regulate population growth. A big part of population growth is reproduction and the ability of a species and individuals to replace themselves. There's a couple terms here that I want to take a moment to discuss. That's R and K selected species. So an R-selected species are species that rely on a really high reproductive rate to overcome high mortality rates. There's very little investment in the young, and they just produce a whole lot of young with the hope that a few of them will survive. So a clam, for example, can produce millions of eggs, and the probability of any one of those eggs surviving is really, really small. But instead of putting a lot of resources and a lot of effort into taking care of a few eggs and making sure those mature, they put their resources into just producing lots and lots and lots of eggs and hoping that a few of those survive to maturity. This is an example of an R-selected species. Other things would be like the salmon. The salmon lay hundreds or thousands of eggs. Once they laid an egg, there's no more investment in it. Most insects are R-selected species. These produce lots of young, but the probability of any young actually surviving is really small. The opposite of that would be K-selected species. Remember, K is the notation we use for carrying capacity. So these are species that have few offspring. The growth rate slows down as they approach a carrying capacity. They have few offspring, but there's a lot of investment in those offspring, and the offspring have a pretty high likelihood of surviving. An elephant. An elephant produces one offspring every 4 to 5 years. The probability of that elephant surviving to adulthood is pretty high. They put a lot of effort into nurturing and taking care of that individual, so they have a really high probability of surviving. Humans are like that. We don't produce a whole lot of offspring, but the offspring we do have a really high probability of actually surviving. So a K-selected species would be those species that have few offspring, but those offspring have a higher probability of surviving. This table comes from your textbook, and it has some generalizations about R-selected species versus K-selected species. These are terms I do want you to know that will show up on an exam at some point. It's good to know what R-selected and K-selected mean. So I'll just talk about a few of these because you can read these on your own as well. Those R-selected species typically have a short life. Think about things like insects, versus K-selected species have a long life. The R-selected species typically grow really fast, where K-selected species grow slow. R-selected species are able to reproduce very quickly, like cockroaches can reproduce after 3 months, versus K-selected species reproduce later in life. There's many offspring with R-selected species versus a few large offspring for K-selected species. Often the R-selected species are those species that are prey for other animals, versus the K-selected species are typically predators. Think about wolves and coyotes and bobcats and mountain lions and things. These are animals that have a few young that have a high probability of surviving, versus rabbits that have lots and lots of young with a lower probability of surviving. Typically, those R-selected species are lower on the food chain as well. We would call that a trophic level. These food chains and food webs, the closer you are to the producers, that would be a lower trophic levels, versus a high trophic level is moving higher and higher up that food chain. All right, and lastly for today, talk about some of these factors that affect growth rates. We often put these into complicated population models. In my career, I've produced lots of population models and trying to predict what populations are doing, how they respond to potential actions. Some of these are really, really complex. I've been to court many times over these sorts of things. The population models really can be broken down into something fairly simple. And that would be what we call a BIDE model, B-I-D-E. So a population and the potential for a population to grow is dependent on inputs and outputs. So BIDE stands for B stands for births, the number of individuals coming into a population. I stands for immigration. These are animals that are coming into the population. Minus D, which are deaths, the animals leaving the population, and immigration, which are animals that are leaving the population, like just moving out of the area. At a basic level, most populations can be broken down like this. And another way to think of it might just be like a checking account. How fast your checking account or saving account changes is really a function of how much money is going in versus how quick is money coming out. And it's the exact same thing happens with populations of wild animals and of living organisms. So with that, I think this is a good point to stop for today. On Monday, we're going to talk a little bit about survivorship curves and then talk some about conservation biology and some issues with conservation biology. So with that, please do look through your book on chapter 6. If you haven't done that homework yet, we don't need to finish these lectures for you to do it. The questions for that homework are coming from this chapter, are coming from these issues. So looking at those now might help you to understand these a little bit better. No need to push it off. You do have through Friday if you need to. Okay, have a good weekend. Be safe. I understand you guys get to go off campus, so be safe out there. Try to stay healthy. And again, if we have any weather issues come up in the future, be safe. That's my highest priority and concern for you. Thank you. Have a good night. Have a good weekend.